Welcome to all ASquare Maths by A2E2. Let us study Laplace transform. Definition of Laplace transform. Let f of t be a function of t for all positive values of t. Then Laplace transform of f of t is denoted by L in the curly bracket f of t and is defined as integration from 0 to infinity e raised to minus st f of t dt, provided that integral exists. The meaning of provided that integral exists that there are some of the functions of t for which Laplace transform doesn't exist, that is integral doesn't exist. Here s is a parameter which may be real or complex. Therefore, Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt. Let us study linearity property of Laplace transform. The statement of the linearity property is let a, comma b and c are constants and f of t, g of t, h of t are functions of t, then Laplace transform of a f of t plus b g of t plus c h of t is equals to a Laplace transform of f of t plus b Laplace transform of g of t plus c Laplace transform of h of t. Let us take a proof. By definition of Laplace transform of f of t is given as integration from 0 to infinity e raised to minus st f of t dt. Therefore, Laplace transform of a f of t plus b g of t plus c h of t is equals to integration from 0 to infinity e raised to minus st a f of t g of t into b plus c h of t dt. By the linearity property of the integration, this term can be written as a integration e to the power minus st f of t dt plus b integration from 0 to infinity raised to minus st g of t dt plus c integration 0 to infinity e raised to minus st h of t dt. But if you observe, by definition of the Laplace transform, whatever the integration e to the power minus st f of t dt, it is nothing but Laplace transform of f of t. This term integration from 0 to infinity raised to minus st g of t dt is nothing but the Laplace transform of g of t, and integration from 0 to infinity e raised to minus st h of t dt is nothing but the Laplace transform of h of t. Hence, this can be written as, by using of Laplace transform, L of Laplace transform of a f of t plus b g of t plus c h of t can be written as, can be equal to a L of or Laplace transform of f of t plus b Laplace transform of g of t plus c Laplace transform of h of t. Let us take Laplace transform of some standard functions. First, Laplace transform of 1 is 1 upon s, where s is greater than 0. Let us prove it. Proof by definition of Laplace transform. Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt. F of t will be replaced by 1. Hence, Laplace transform of 1 is equals to integration from 0 to infinity e raised to minus st dt. And integration of e raised to minus st is equals to e raised to minus st upon minus s and limits from 0 to infinity. That is equals to minus 1 upon s and putting limit, upper limit e raised to minus infinity minus e raised to 0. Here e raised to minus infinity can be written as 1 upon infinity and e raised to 0 is as it is. Therefore, Laplace transform of 1 is equals to minus 1 upon s, 1 upon infinity minus 1, and it is equals to 1 upon infinity can be written is nothing but the 0, and that is equals to minus 1 upon s into 1 minus 0 minus 1. Therefore, Laplace transform of 1 is equals to 1 by s. Laplace transform of some standard functions. Let us take Laplace transform of k, where k is a constant, is equals to k upon s for s greater than 0. Let us take a proof by definition of Laplace transform. Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt. Therefore, Laplace transform of k, f of t will be replaced by k. Laplace transform of k is equals to integration from 0 to infinity k e raised to minus st dt is equals to k integration e raised to minus st, as far as k is a constant, e raised to minus st upon minus s. Limits will be from 0 to infinity. Taking constant factors outside k minus 1 upon s and putting the limit e raised to minus infinity minus e raised to 0 is equals to k into minus 1 upon s. E raised to minus infinity can be written as 1 upon e raised to infinity minus e raised to 0. 1 upon e raised to infinity, here we have taken 1 upon infinity minus 1 is equals to minus k upon s. 1 upon infinity is nothing but 0 and e raised to 0 is minus 1, as it is we have taken, and hence by simplification you will get here Laplace transform of k is equals to k by s. Third standard function, Laplace transform of e raised to at is equals to 1 upon s minus a, where a is a constant such that s should be greater than a. Let us take a proof by definition of Laplace transform, that is Laplace transform f of t is equals to integration from 0 to infinity e raised to minus st f of t dt. Therefore, Laplace transform of e raised to at is equals to integration from 0 to infinity e raised to at into e raised to minus st. By the law of indices, in the next step, this is equals to integration from 0 to infinity e raised to at minus st. This term indices can be written as e raised to minus s minus at dt. Taking integration with respect to t, this is e raised to minus s minus at upon minus s minus a, and limits will be from 0 to infinity. Taking constant term 1 outside, minus 1 upon s minus a in the bracket by putting upper limit e raised to minus infinity minus e raised to 0. That is equals to minus 1 upon s minus a, 1 upon e raised to infinity, e raised to minus infinity can be written as 1 upon e raised to infinity minus e raised to 0. Therefore, Laplace transform of e raised to at can be written as minus 1 upon s minus a in the bracket 1 upon infinity minus 1. But 1 upon infinity is 0. So that is equals to minus 1 upon s minus a in the bracket 0 minus 1. Therefore, Laplace transform of e raised to at is equals to 1 upon s minus a. Fourth one, Laplace transform of t raised to n is equals to gamma n plus 1 upon s raised to n plus 1, where n is a real number such that gamma function of n plus 1 exists. Proof by definition of Laplace transform. Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt. Therefore, Laplace transform of t raised to n is equals to 0 to infinity t raised to n e raised to minus st dt. Here we want to find this integral. To find this integral, let us put st is equals to u, therefore s dt is equals to du. It implies that dt can be replaced by du upon s. As t varies from 0 to infinity, u will vary from 0 to infinity. By putting entire values in terms of u of t, you will get Laplace transform of t raised to n is equals to integration from 0 to infinity u by s to the power n e raised to minus u du upon ds. As terms taking outside, you may get here 1 upon s raised to n plus 1 integration from 0 to infinity u raised to n e raised to minus u du. But if you observe, this integral is nothing but the gamma function of n plus 1. Hence, this integral will be replaced by gamma function of n plus 1. Hence, you may get here Laplace transform of t raised to n is equals to gamma n plus 1 s upon s raised to n plus 1. By gamma function, you may get this one. Fifth one, Laplace transform of sin of at is equals to a upon s square plus a square. Again, proof by definition of Laplace transform of f of t is equals to 0 to infinity e raised to minus st f of t dt. Therefore, let us replace f of t by sin of at. Therefore, Laplace transform of sin of at is equals to integration from 0 to infinity e raised to minus st sin of at dt. The integration of sin of at into e raised to minus st is given by e raised to minus st upon minus s the whole square plus a square in the bracket minus s sin of at minus a cos of at. Limit will be from 0 to infinity. By putting upper limit and lower limit, confidently upper limit will be a 0 and lower limit will be a minus 1 upon, because e to the power 0 is 0, 1 upon minus s square plus a square as it is. Sin of 0 is 0 and minus a cos of 0. Cos of 0 is 1 and further minus minus will become plus, and that one will be the required result. That is Laplace transform of sin of at is equals to a upon s square plus a square. Next, let us see Laplace transform of cos of at. Laplace transform of cos of at is equals to s upon s square plus a square. Proof by definition of Laplace transform. Integration from 0 to infinity e raised to minus st f of t dt is the Laplace transform of f of t. Therefore, Laplace transform of cos of at is equals to integration from 0 to infinity e raised to minus st cos of at dt. By taking the integration of e raised to minus st cos of at with respect to t, we get Laplace transform of cos of at is equals to e raised to minus st upon minus s square plus a square minus s cos of at plus a sin of at. Limit will be from 0 to infinity. Putting upper limit and lower limit, here Laplace transform of cos of at is at cos of at is equals to 0 minus 1 upon minus s the whole square plus a square minus s cos of 0, because sin of 0 is 0. And final answer is therefore cos of at is equals to s upon s square plus a square. Last, Laplace transform of hyperbolic sin of at. Laplace transform of sin of AT, hyperbolic sine of AT is equals to A upon S square minus A square for S greater than mod of A, where A is a constant. Let Laplace transform of hyperbolic sine of AT is equals to Laplace transform of e to the power AT minus e to the power minus AT by 2. Therefore, 1 by 2 Laplace transform of e to the power AT minus e to the power minus AT. Therefore, by linearity property, this can be written as Laplace transform of hyperbolic sine AT is equals to 1 by 2 Laplace transform of e to the power AT minus Laplace transform of e to the power minus AT, but Laplace transform of e to the power of AT is nothing but 1 upon S minus A, and Laplace transform of e raised to power minus AT is 1 upon S plus A, and hence by adding both the fractions you will get their cross multiplication. Laplace transform of hyperbolic sine of AT is equals to 1 by 2 in the bracket S plus A minus S minus A upon S plus A into S minus A. S and S will get cancelled. You will get there 1 by 2 2A upon S square minus A square, since S plus A into S plus minus A is nothing but the S square minus A square. Therefore, it implies that Laplace transform of hyperbolic sine of AT is nothing but A upon S square plus A upon S square minus A square. 8. Laplace transform of hyperbolic cos of AT is equals to S upon S square minus A square for S greater than mod of A, where A is a constant. Proof. Let Laplace transform of hyperbolic cos of AT is equals to, let us, whatever the hyperbolic term, we will transform it into the exponential form. Therefore, Laplace transform of e to the power AT plus e to the power minus AT by 2. 1 by 2 is constant, we may take that outside. So, 1 by 2 Laplace transform of e to the power AT plus e to the power minus AT. By linearity property, therefore, Laplace transform of hyperbolic cos of AT is equals to 1 by 2 in the bracket Laplace transform of AT plus Laplace transform of minus e to the power minus AT, and that is Laplace transform of hyperbolic cos of AT is equals to 1 by 2 in the bracket 1 upon S minus A. Laplace transform of e to the power AT is 1 upon S minus A, and Laplace transform of e to the power minus AT is 1 upon S plus A. Taking addition of both the fractions, you will get 1 by 2 S plus A plus S minus A upon S plus A into S minus A. There, that is equals to 1 upon 2 S square minus A square. And it implies that hyperbolic cos of AT is equals to S upon S square minus A square. That's the to be continued Laplace transform. These are all the standard Laplace transform of standard functions. Thank you.